the chemical change. That's very important, talking about the chemical change, and then talking about when you passing the electric current through the electrode. I state two differences between the anode and the cathode, right? The chemical change, that's very important, talking about the anode is the positive electrode. So the anode is the positive electrode. The cathode is the negative electrode. All right. So it is the positive, the anode, and the cathode is the negative. Okay. So you would say that anions are attracted to the anode and cations are attracted to the cathode. And you get your 2 marks there for those 2 reasons. Then it says, draw a diagram to show a circuit for carrying out this investigation. Label the cathode and the electrolyte. So label the cathode and the electrolyte. Very simple, all right? So what you're going to need your cell, your electrolytic cell, most times being a battery. You put your positive and your negative. We're going to draw that here. Going to draw that here. Now you're going to go down. Okay. So you make your make them a little bigger. Give it a little bigger. Okay. Okay. So that will be the electrolyte. They want you to label it. So you write copper sulfate aqueous. That being your electrolyte here. Then you will label your cathode. You will label your anode. And as far as they told us, the copper electrode, so both of them are Cu solid. Both of these are Cu solid. And that would be what they want you to do for the diagram. So then it says complete table 1 by recording the mass of the cathode after 10 minutes and 20 minutes and the mass of copper deposited after 15 and 25 minutes. Okay. Now, usually for these questions, they tend to give you stuff. But no, they want you to record the mass after 10 and 20 minutes and the mass of copper deposited after 15 and 25 minutes. That we don't do. But what you should notice if you watch the table, it starts at 11.80. However, you will notice that on the second row, that they have 11.83 and 0.03, meaning that 0.03 was added to that 11.80 to make the mass of the cathode. So the mass of the cathode is actually increasing. So what you're going to do now, you're going to add this to the mass of the cathode at 0. All right, at t is equal to 0. So therefore, what we'll have here is 11.85. We'd have 0.07 here. We'd have 11.89, and we would have 0.11. That's what we have here. So now it's saying total graph of actual mass of copper deposited versus time using the axis in figure 1 on page 5. So I'm going to take the table. I'm gonna select the table. I'm gonna select the table. I need to also select the table. So I take in the text. I need to select the text. Here we have the table. I'm gonna draw the graph now. So what CSEC has to do in graphs is that they always give you the axis drawn already. So it's never a case where you have to spend time looking for scales and stuff. You just have to put the paper properly. So we're going to mark it. Remember, you have to be careful. You're depositing a mass of copper deposited. So this column here against time, that's what you're doing. This column here against this. All right, so at 0, we have 0. At 5, we have 0.03. So 1, 2, 3, 4. At 10, we have 0.05. 15, we have 0.07. So I need an increment of 2.5. Okay, so that's the graph here. Now it's gonna be pretty much look like a line of best fit. You have a line here, so you use your ruler. I don't have a ruler, so I need to, so I'll use this. So this is essentially what your graph should look like. And then the next part of the question asks us to use the graph to predict the mass of copper that will be deposited after 28 minutes. So we'll extrapolate our graph to go past 28 minutes. And so at 28 minutes, we have just about, my mistake there. Yeah, 28 minutes. A 0.12, right? So you get 0.12 grams. And then part 7 is write an ion equation to represent the reaction at the cathode. Now, because it's depositing, we're going to have now that Cu, we have reduction occurring at the cathode. So that's reduction is gain. So that's aqueous. And again, 2 electrons and form copper solid. Okay. So that's what we see. So based on that equation, we have 2 electrons are involved. So we'll calculate the quantity of electricity that passed through the copper sulfate when the current flipped for 20 minutes, knowing that, right? Now, remember, Faraday's constant is per mole of electrons, right? And in the reaction we have discovered, we know it's 2 electrons, right? So we're looking at the of cathode, right? Because that was the part of the action we had in it, right? So let us go ahead. The current is 0.2 amperes. The time in seconds, right? So remember to get your time in seconds. That's equal to 20 times 60. It's equal to 1200 seconds. Okay. Therefore, Q is equal to IT, so 0.2 times 1200, which should be 240 coulombs, yes. And we know from the equation that 2 moles electrons are required to, oh, sorry, I went too far. They give you Faraday's constant, but you don't need it right now. So all you need is just 240. So the equation, and then you see there, that according to the equation, that 2 moles of electrons required to form 1 mole of copper. Therefore, 2 times Faraday from 1 mole, and therefore you can put that number to 190,000 coulombs. And you're going to link it to the charge now to find the number of moles of copper, right? So you know that. So 1 coulomb forms 1/19 and 240 coulombs forms 240 times 1/19,000 coulombs. You put that in your calculator. And you will get 0.0012 moles copper. And now to calculate the mass of copper that would be formed, you're going to multiply the number of moles by the mass. And you should get 0.08 grams of copper, right? So it's a suggested reason for the difference between the mass of copper obtained in X. Now, at 20 minutes, you have 0.08. At 20 minutes, you have 0.09. So that means your answer you just calculated has to be correct. But now it's telling you, how comes in the table you have 0.09 and 0.08? Now, this partner is asking you for like sources of error, okay? Sources of error, pretty much. Now, in a question like that, the biggest source of error you would involve is with the experiment itself, right? Because listen to what is happening, right? The citrus of the cathode was removed, rinse with distilled water, dried in air, and then weighed again. Now, copper can oxidize, right? So it is possible that when you take out the copper to do the experiments to wait, that it's oxidized, it is left to the air and it is oxidized. So copper is lost during the experiment, right? So copper is lost during the experiment. So if you can explain that to get your mark, it's lost during the experiment. Because the fact you're taking out copper, it's oxidizing back, which means you're losing. So by the time when you put it back, you have less and less and less. All right. And then it says the circuit used in this experiment was modified by replacing the copper electrodes, graphite electrodes. Now, graphite electrodes are inert, okay? So it says state one difference in the reaction at the anode when graphite electrodes are used. Now, previously at the anode, what we have is oxidation of copper, right? That the copper, this is what will happen to copper. But now in solution, what we have is we have copper, we have sulfate, and then we have hydrogen, and then we have this. So if we change now to inert electrodes, what's going to happen at the anode, that the OH ions will be preferably discharged, preferentially discharged. Okay? They'll be preferentially discharged. And that's that, okay. We just did this before the qualitative analysis questions. We'll pass that straight. But I want to go to question number 2 because we just looked at bonding. So we're going to look at how CSEC sometimes ties it in, okay? So it says, depending on their structures and properties, solids may be classified as having metallic, giant covalent, simple, molecular, or ionic lattice structures. The structure and conductivity of selected solids will be summarized in table 3. So there's complete table 3 to show the structure and conductivity of each solid substance state. The first one is done as an example. So they tell you magnesium chloride, structure ionic, conducts electricity in solid state. Fine. Iodine, we should be aware that iodine is covalent, it's a non-metal, it's a covalent structure. Does it conduct electricity in solid state? No, it cannot. Zinc, on the other hand, zinc is metallic. All right. Oh, they ask for to be specific between giant covalent and simple molecular. So all these things are things to pay attention to. So for iodine, it would be covalent, but it would be simple molecular. So these are important to pay attention to. No, all right. Zinc is metallic. Yes, it will conduct electricity in solid state. Diamond is giant covalent, and it does not conduct. So it gets 6 marks, 1 mark for each correct answer. And then you got a question about solubility, right? Magnesium chloride and potassium nitrate have ionic lattice structures. Figure 2 on page 9 is the next page there, shows solubility curves for magnesium chloride and potassium nitrate. Use the information in the graph to answer the questions below. Which of the two compounds, magnesium chloride or potassium nitrate, has the greater solubility at 15 degrees Celsius? So you go to your graph, you look for it at 15 degrees Celsius. Okay. Look for it at 15 degrees Celsius for both of them. So you can extrapolate the interpolate the lines. That's that. There's a different color. 15 for you too. Where it intersects the graph. So at 15 degrees Celsius. So that's how you do that. That's what you go about doing that. Okay. So the solubility of the potassium nitrate, so that's potassium and that's magnesium. So which one has a greater solubility at 15? Magnesium chloride would have a greater solubility at 15. So MgCl2. Calculate the mass of potassium nitrate that would be deposited when a saturated solution is cooled from 80 degrees to 20 degrees Celsius. So 80 degrees, 20 degrees Celsius. So we're looking at here between 80 and 20, right? So it's for potassium nitrate. We're going to draw a line from this 80 line here. We're going to check the mass. Very easy. That's already per 100 grams of water, so that's fine. So that's at 80, and then at 20. Okay, so we're going to do the difference. So that's 1, 2, 3, 4, 5. Each point is 0.2. So here we have 14.4 grams. And here we have 7.6 grams. So to get the answer, it would be 14.4 grams minus 7.6 grams. So you take a look at from the points, and that answer should be 6.8 grams. Okay. And it says determine the temperature. So using a graph for this question, determine the temperature at which solubility of magnesium chloride and potassium nitrate are equal. Yeah. So this point where they intersect, that's where you're going to to draw it where they intersect with each other. So this line here, where they intersect with each other. So if you put anywhere between 10.8 and 11.2, sorry, the temperature. So 58 degrees Celsius will be the temperature. So that's a nice little question. And then C comes back to bonding, which we were talking about a while ago. It says draw the bonding diagram to show magnesium combines with chlorine to make magnesium chloride. So that's ionic bonding they want us to do. So remember, we have two steps we have to show. Magnesium has a 2+ charge. So I'll only use the valence shell because you are allowed to draw if only the valence shell. So I'll use the valence shell. Magnesium. And it's dot and cross diagrams. So remember, one has to be a dot, the other one has to be a cross. Okay. You don't want to use marks for silly mistakes like that. You want to get all your marks you can get. So that's what we have here. Now, this is not so necessary because it's only with 2 marks, and because it's the exam, they don't expect you to draw all of this. So it's only if you need, honestly, to remember what exactly you're doing. But it's what I'm about to put here on this side that is really important, right? So the magnesium, of course, the right charge, and then the chlorine, of course, having the donated electron. And if you draw them around the magnesium, that's fine too. You just need to make sure you have the right arrangements and the right charges. So that would be your max for your bonding. And then based on the use and purpose of solid air fresheners, would you classify them as having a simple molecular, giant covalent, or ionic lattices? Explain your answer. Solid air fresheners. What do you guys think? Is it simple molecular, giant covalent, or ionic lattices?
Sorry, could you say that again?
What do you think they are? Do you think they are simple? Is that simple?
Yeah. Yeah, it's simple.
I think they're simple too. Because air fresheners, the major thing we have to look at is volatility, right? They're solid air fresheners. However, they have to go to gaseous form. They have to The reason why is because they have to go to gaseous form, right? As air fresheners, they need to easily convert to gaseous form.
Okay, I found this on the web for I need to easily come.
Therefore, the intermolecular forces must be weak. Must be weak, and the BP must be low. Okay. The same thing with fingers. Okay. Must be low. Therefore, it is simple molecular. So you'd have to explain that to get your free marks. There's an air freshener. You want to get it to the gaseous form as fast as possible, as quick as possible. So it would have to be that, okay? Because we want to get the conversion, it has to have a very low, relatively low boiling point, and that would be that. So we've done 2 of the first set of questions from this paper. It's a very nice paper. I like this paper. Okay. So we have done this. Okay. So we looked at one example of electrolysis. I am going to put another example, because as I mentioned, things are different, right? And some of the questions will ask you to compare, etc., etc., etc. And I want to make sure we are all ready for whatever CXC will decide to throw at our way. Now, it's been a while, so we've gotten a solubility question. I mean, we just did one a while ago. It's not that difficult, but you might get solubility too, just thinking about it. But I think they have decided maybe not to do that anymore with the paper tools. I think they've made a move away from doing that. Okay, get electrolysis for you. But past papers, do many past papers as you can before the exam. Do as many as you can. That's the only way you'll be properly prepared. And we are going to do paper 1 this afternoon. Okay, I got another question for you. This is a January paper. So it'll be slightly different. Let me know if you can still see my screen.
Yeah, we can.
I can see a screen.
All right, great. So here it says, the process of electrolysis has a number of useful applications during the purification of copper. So again, I tell you that they love to talk about copper. Especially electrodes are used to give the desired products. So the finite term electrolysis, we just looked at that a while ago. So electrolysis is the chemical change occurring when an electric current, I need to change my end. When an electric current is passed through an electrolyte. So it's still the type of analog that is used in purification of copper. Because it is the purification of copper, it will be an active electrode, because you'll have copper at one end. You'll have two coppers, right? So you'll have you're going to want it to deposit copper at the other end. There's a copper anode. Right. Next part says figure 2 depicts the apparatus used to electrolyze a sample of molten lead bromide. Now we should know the differences between molten and aqueous or ionic electrolysis. We should try to remember. So it contains two different ions, only the cation and the anion. So the only ones you would have would be lead 2 and bromine minus, right? The one in the ionic electrolytes, these are the ones where you will have two different types of ions, the ones from the water and the one from the compound itself. But in this case, we're just dealing with two electrodes, which is really nice. So it says, which of these electrodes in the diagram is the cathode? So the cathode is a negative electrode, so it would have to be electrode number 2. And it says, what is the formula of the ion that migrates towards the anode? So the anode would migrate, take the negative ion. So therefore it would be bromine that migrates towards the anode. So nice little question. And it says, write a balanced ion equation for the reaction occurring at the cathode. So at the cathode, we're going to have the lead accepting these electrons to become lead solid. That's the equation. And then we have a quantitative part again. A current of 5 amps is passed through the molten lead bromide for 5 minutes. Let's convert that 5 minutes. Calculate the mass of lead. So now it's tying in everything. That will be deposited, and they give you the relative atomic mass. So Q is equal to IT first. We know that. So it would be 5 times 60, which is 300. So it'd be 1500 coulombs. And then again, we will state that 2 moles, no, 9650 produces 2 moles. So 1 mole of lead needs 2 electrons. That's what you write. And therefore, 1 mole of lead needs 19 coulombs. And because we only have 15,000 coulombs, therefore, That's coulombs per mole. Eh? So what you want to do is get 2 moles. So we are going to divide that 15 number of moles at 15,000 coulombs by this. That is 0 coulomb per mole. We'll get our answer, which is calculator. 15 0.008 moles, and now we want to find the mass, which will be equal to that 0.008 times 207, and for our mass we will find 1.65, well, 1.66 grams of lead. Okay, and that will be your 4 marks. So then the next one deals with reactivity series of metals. So it says a zinc rod is immersed in a solution of magnesium sulfate. A zinc rod is immersed in a solution of copper sulfate. In experiment 1, no visible change was observed, while in experiment 2, a brown solid settled to the bottom of the container. So that tells you. Explain the observations from both of the experiments. That should be 4 marks. Yes. So let us go over the reactivity series of metals. And there's a nice little acronym we had said at the beginning of class when we were talking about mnemonics, right? So we said that Peter sometimes collects money at zoos, so I remember, in London for helping crazy monkeys and silly giraffes. That's the acronym. And each of these stand for a metal, right? So P would stand for potassium, meaning most reactive. S, sodium. C here would stand for calcium. M, magnesium. A, aluminum. So I don't know if I ever taught you all this, but this is a nice way of remembering it. Zinc. And you need to know this for electrolysis too. This is why it came in the question, because you need to know what to preferentially discharge over the other in terms of cations. Anions depend heavily more on the type of electrode, but in terms of cations, that is what would be the electrical series, to be honest. It's not even that to say that. That's for metals as a whole. It's for metals as a whole. Iron, hydrogen, copper, mercury, silver, and board. Okay, so based on that, let's look at our series. We have zinc and magnesium. Magnesium is on top of zinc. So therefore, there will be no visible change, right? So magnesium is above zinc in the reactivity series of metals. Therefore, Mg will not displace zinc. From the zinc sulfate. And experiment 2 will say that zinc displaces copper from the solution as it is more reactive. Okay, as it is more reactive. Okay, as it is more reactive. Now, in terms of the electrolysis, things change a little bit from this order. It's not a big change, but it happens just because of that, right? So let me tell you. Calcium moves up here, right? We're dealing with cations. Calcium moves up. So they switch places, really. That's the only change. They switch places, okay? They switch places. And you insert lead here. But apart from that, everything else stays the same. The reason for that being calcium is slightly more reactive when it comes to getting rid of both of its electrons at a given time. So the same principle applies with the reactivity series. So the lower the ion is in the list, the most likely it's the easier it is for you to discharge it with something else. But the higher something is the more likely it's going to stay